All right, so I didn't grade your third homeworks yet, so I'm not going to talk about the solution of the homework yet, so I don't know the alternative solutions. So today the plan is to finish partitioning a simple polygon into monotone pieces. I'm going to talk about the details of the algorithm. I mentioned that it's going to be a sweep line algorithm, and we are going to maintain edges and their helper vertices, but I didn't go into detail of this. So today I'm going to finish partitioning any simple polygon into Y monotone pieces, and then we are going to see an algorithm which works in linear time to partition a monotone polygon, Y monotone polygon, into triangles. So then it's going to conclude the polygon triangulation chapter, and then we are going to see today a new problem, which is the casting problem. We are going to see what casting, the geometry of casting, we are going to see about that. And we are going to formulate it as a two-variable linear program. And we'll be able to solve it in linear expected time. So, okay, so it's going to be really, and we are going to see something really interesting. I mean, the complexity analysis that we are going to see is going to involve some probability. So we are going to, I mean, the worst case complexity is going to be O(n) square. The algorithm we are going to see is going to be an O(n) square algorithm. But the expected running time of this algorithm we are going to see is going to be O(n). Okay, so it's very strange. So you are going to see how this is possible, how, I mean, this worst case is less likely to occur. So we are going to see about that. So, okay, so let's start. A simple polygon, it can be a concave or a convex polygon. If it's convex polygon, triangulating a convex polygon is very easy. You can draw diagonals between any pair of vertices. So you can select a vertex, draw diagonals to all the remaining vertices, you triangulate your convex polygon. So imagine we have a concave polygon, which may be very complex, and our goal is to triangulate this concave polygon. And the first step is, can we subdivide this concave polygon into Y monotone polygons? And if you remember, the Y monotone polygons, they have a top, if a polygon is Y monotone, and let's assume for now, for simplicity of understanding, we don't deal with the degenerate extreme cases. So assume that you don't have any horizontal edges in your polygon, okay? That these horizontal edges can be dealt with easily later, but for now you don't need to think about them. So assume a Y monotone polygon has two left and right chains of vertices, okay? And each chain of vertices has vertices that are always increasing in Y coordinates. Okay, so we are going to have vertices like this in the left chain, and we are going to have vertices on the right chain. It can be something like this. This is the last vertex. So both left and right chains, due to its Y monotonicity, their Y coordinates are always, I mean, if you look at the vertices in one chain, the Y coordinates are always decreasing if this is the positive Y axis. Okay? So first of all, I mean, if we have a polygon like this, we'll be able to triangulate this polygon in linear time. So if we can divide our simple polygon into Y monotone polygons like this, this Y monotone polygon can be triangulated easily in linear time. Again, using a sweep line, plane sweep algorithm. So plane sweep algorithms is used everywhere. So first, before seeing how this is triangulated, our first problem is how do we divide our general polygon, which could be something like that. For example, at that point, we could have, so this is a simple polygon. Okay. which is not Y monotone. Okay, so you don't like this sound of it, so I'm going to change the pen. So this is not a Y monotone polygon, so we need to decompose this into Y monotone pieces, and we remember we identify certain types of vertices in this simple polygon, which are split vertices, merge vertices, start, end vertices, and regular vertices. Here, I mean, this chain, as you can see, is a nice regular, I mean, it's a Y monotone chain, okay? It's Y monotone because there is no vertex in which, I mean, for any vertex on this chain, both of its neighbors are, one of them is at the top, the other is at the bottom, okay? If both of the vertices both of the neighbor vertices of a vertex like this, look at this one, both of its neighbors are at the top, meaning that we are not seeing a decrease in Y coordinate monotonically. So therefore, we need to get rid of this vertex, and we need to change its type. So at that point, so the type of this vertex is a merge vertex. Okay, it's a merge. We call it merge vertex because we need to draw a diagonal to another vertex that come after it. Okay, merge vertices are vertices in which both its neighbors are higher than that vertex, and the inner angle. So this is the inner part of the polygon. Okay, that inner angle is greater than pi. Okay? If it was less than pi, if the inner part of the vertex was here, this would be an end vertex. It would be the end of a polygon. So we don't need to do anything at end vertices. The problematic vertices are merge and split vertices. For example, this is a merge vertex, and here this is a split vertex. Split. And this is merge vertex. And split vertices, here again, you see there's a problem. Both of its neighbors are below it, okay? So we don't again see these two neighbors. We don't see a regular increase in Y coordinates when we look at its neighbors. So again, we need to draw a diagonal. In this case, we need to draw it to make this a regular vertex. We need to draw a diagonal to some other vertex that is above it. And if we do it, for example, if we draw a vertex, draw a diagonal to this one. So if this becomes our diagonal, as you can see, this vertex becomes a regular vertex in both parts, both in the new polygon on the left and both on the polygon on the right. This becomes a regular vertex because we see a regular decrease in Y coordinate in both polygons. So if we draw a diagonal to a vertex that is higher than the split vertex, we'll be able to make the split vertex a regular one. So, and our goal in this algorithm will be to get rid of all merge and split vertices. And there's a lemma about this in the book that says that if a polygon is it's a vice versa actually. If there's a split vertex or a merge vertex in a polygon, then it's not Y monotone. Okay? So it means that if we can get rid of these merge and split vertices, we are going to make it a Y monotone polygon. So that's the main idea of this algorithm. To make it Y monotone, we need to get rid of merge and split vertices. Okay, now the problem, we actually talked about the solution. In order to get rid of these split and merge vertices, we need to draw diagonals. Now, for split vertices, we draw a diagonal to another vertex of the polygon that is higher than the split vertex. And for merge vertices, we need to draw a diagonal for a vertex that is, for example, to here, that has a smaller Y coordinate than that vertex, okay? So for merge vertices, our diagonal will go down. For split vertices, our diagonals, the new drawn diagonals, will go up. Now, In this algorithm, we need to discuss this. Which vertex, which vertex I'm going to choose to draw this diagonal? In that regard, what should I be careful? I mean, can you choose any vertex to draw the diagonal, any vertex that is up? For example, what is wrong with this vertex? I cannot, so it's obvious because it intersects with the, it doesn't, with the polygon edges. The definition of a diagonal is the diagonal should be completely inside the polygon. Okay, so this vertex is not a very good vertex. I mean, the first vertex really was a good candidate. So also, I can also draw one to here actually. This is also valid diagonal, this one. So how do you choose this vertex? That's the next thing that, when you're designing this algorithm, that's the next thing you need to solve. How do you choose a vertex that you guarantee that it's not going to intersect any other polygon edges? So it should be, for example, if I choose a vertex that is close to me, I mean, there's a higher chance of non-intersecting, right? I mean, far away vertices from me have a larger chance of intersecting other polygon edges. And I don't want to leave this to chance. I mean, closer vertices have low chance of intersecting with another diagonal, but I want to reduce this chance to 0. Can you select a vertex in which you are going to be sure that the diagonal that you draw to this vertex is going to be inside the polygon? Okay? Now, this is what you do in the solution. For a given vertex, you look at its left neighbor. You look at this edge here, the edge that is the left neighbor. And this, when I say left neighbor, as you can see, this edge does not have any connection to this vertex actually. I mean, it's not. It's not a neighbor on the polygon. It's a neighbor edge during plane sweep. Okay, the sweep line. If you imagine this sweep line is at this split vertex. Okay, we have a sweep line at this split vertex. Okay, at this point, at this event point, I can query if I have a binary search tree of edges that intersect the sweep line. All these edges are ordered from left to right on this binary search tree that intersect the sweep line. And on this sweep line, I can query the left and right neighbors. So this is going to be the left neighbor. This is going to be the right neighbor of this split vertex. Okay, let me name them EI and EJ. Okay, so I have two neighboring edges that are neighbors to this split vertex. They are not neighbors on the polygon. I mean, this vertex is not incident to them. Let me rephrase that. Okay, this vertex is not incident to EI or EJ, but when the sweep line reaches this point, the edge immediately to the left of this vertex and the edge immediately to the right of this vertex on the sweep line is EI and EJ. Okay, are EI and EJ edges. Okay, I'm trying to define my algorithm right now. Let's look at these two edges. Okay, first, let's look at these two edges. Now, any vertex that is closest to the sweep line and above the sweep line and between these two edges, EI and EJ, is guaranteed to give me a valid diagonal. So that's the main key point in this algorithm. So I'm going to look at the vertices between these two edges. For example, these two can be considered between. This can also be considered between. I mean, you can look at the endpoints. I mean, just look at a vertex between these two edges, EI and EJ. And the lowest of these vertices between EI and EJ that I currently, up to this point that I currently found, is going to be the closest vertex to the sweep line. I mean, this region here is my safe region. If I have a vertex in that region, since this is the leftmost, the left neighbor edge and the right neighbor edge, it means that there are no edges in between these two edges, okay? On the sweep line, this is the left neighbor and right neighbor. It means that there are no other edges in between. These are the closest left neighbor, closest right neighbor edge. So any vertex in between above the sweep line is going to be a safe vertex for me to draw a diagonal to. Okay, so that's the main idea. And how do we know this vertex? For example, right now this is that safe vertex. The lowest vertex here is this. Between EI and EJ, the lowest vertex is this vertex. Let's name it VJ. Okay? Now this VJ, or let me name it VK, not to mess with these indices. This vertex VK is neither incident to EI nor EJ. Okay? This is completely unrelated to EI and EJ. It's somewhere in between. It's incident to this. So how are we going to find this safe vertex? So that's going to be the next issue. And what we are going to do is, we are going to find these vertices during plane sweep. I don't need to find it out when I come to this vertex. Actually, during sweep line, when I come to VK, then when the sweep line reaches VK, it's going to become the helper vertex of its leftmost neighbor EJ. Okay? It means that since when my sweep line reaches VK, when I'm coming from top, when I come to VK, I see that my leftmost neighbor edge is EI. And it means that I can draw, it means that this line here, this horizontal line here, does not intersect any other polygon edges. That's why, because EI is going to be the leftmost neighbor and the closest neighbor on the left to VK. So here, when I reach VK, I'm going to set the helper vertex. So that's the definition, formal definition of helper vertex. The helper vertex of this edge is going to be set to this event point VK. So during plane sweep, I maintain two things in my study structure. First, the edges that intersect the sweep line. Second, for each of these edges, I maintain their helper vertices. And these helper vertices may dynamically change. For example, before I come to this point VK, let's have this VK. Before I come to this VK, when the sweep line is here, okay, let's go further back. Now, when the sweep line reaches the end point of this EI, I don't know VK yet, okay? I am right now at the end of EI. At that point, its helper vertex is top vertex of this edge. So one of its vertices, incident vertices, can be a helper of this EI. So when I first meet EI, when I come to this event point, I initially set its helper vertex to its top vertex here. So this one here is EI's initial helper vertex. But when I come afterwards, when I come to this VK during plane sweep, I see that VK's left neighbor is EI, and I change the helper vertex of EI, I cross this part out, and I set it to VK. So dynamically, for example, when there's a new vertex here, okay, when there's a new vertex here, and at some point this EI becomes the left neighbor of this new vertex on the sweep line, I again update the helper vertex of EI to be this one then. So at each event point, I maintain the correct, the list of edges that intersect the sweep line, and also for each of these edges, I correctly maintain their helper vertices. So when I come to a split vertex during plane sweep, I can safely, all I need, the thing I'm going to do is going to be very easy. When I come to a split vertex, I find my left neighbor and I draw a diagonal to its helper vertex. Okay, so it's going to be that easy. I mean, when you come to a split vertex, you can now safely, since the helper vertex is already dynamically updated, you look at the helper vertex of your left neighboring edge and draw a diagonal to that edge. It can be either this one at this point. This is going to be the helper of EI if we have such vertex there. Now, that's for split vertices. Any questions about split vertices and helper vertices of edges? I mean, you can ask, for example, why do we choose left edge? Okay, why do we choose the helper of left edge? Why not right edge? It could have been done. I mean, it's not a unique algorithm. You could have. I mean, it's just that you have to choose one of the edges. I mean, it's the helper of leftmost edge is going to be here. You could have choose your rightmost neighbor, and you could have set helper of rightmost edges as well. I mean, you could have modified the algorithm to do that. They're indifferent. I mean, they are going to provide the same results. But you only need one of them. You don't need the helper of two. I mean, you only need to find yourself a single vertex that is safe, and this is how you choose it. You could have chosen it differently by looking at your right neighbor and setting the helper of your right neighbor. I mean, this algorithm chooses to use the left neighbor and the helper of left neighbors, and actually afterwards we see that this choice, by just looking at the left neighbors, we see that we don't need to store edges in which the polygon lies to their left. I mean, for example, we only need to store edges in which the helper vertex is to their right. I mean, not all the edges of the polygon need to be stored in the study structure. Because this one, for example, look at this edge here. Can it be a left neighbor of an event point? Never. Because this part is outside of the polygon. So it can never be the left neighbor of an event point. So since in this algorithm we are always going to be querying what is my left neighbor and what's this helper vertex. So we are going to be always querying the left neighbors. So we don't need to even store edges that are guaranteed to be no left neighbors. So such edges in which globally, if the polygon is lying to their left in this global orientation, we don't need to store those edges in our study structure. But if you have chosen otherwise, if you have chosen to look at the right neighbor and choose its helper vertex, then you would do it otherwise. So this is just a decision you make when you design your algorithm. But you need to prove its correctness to have a correct algorithm. Any questions? Okay, I asked the question, I answered it myself. So why do we use left and right? So if you have other questions, you can also ask them. And now we are done with split vertices. But now, if you come to merge vertices, we have a problem. Okay. Now we said that merge vertices, we need to draw a diagonal to a vertex that is lower than that. But we are doing plane sweep. Okay. When I come to this merge vertex, I have no information about what is under me. Okay. That's the main thing about plane sweep. You have processed everything that are above the sweep line, and you don't have any information about what is going underneath the sweep line. Now that's the problem with merge vertex. Okay, when you come to a merge vertex, you see that you cannot find the diagonal at that point. You cannot draw the diagonal at that point. But this problem, which seems difficult at first, actually can be solved easily later, because this merge vertex, we don't need to draw the diagonal at that point. But when we come to another vertex, and we see that, for example, what happens is that this vertex, which is safe to draw a diagonal from that merge vertex, we see that if, for example, look at this edge now, let's name it EW. This EW becomes the helper, this merge vertex here becomes the helper vertex of EW when we come to this merge vertex. And either what we can do is, at that point, let's draw this a little bit higher to demonstrate what I'm trying to tell you here. Okay, if there's another vertex which replaces this merge vertex as the helper of EW. Okay, if I update EW's helper vertex with this new vertex, what happens is that this new vertex is the diagonal that I want to draw to this merge vertex. So if EW, when its helper vertex is updated, if the previous helper vertex was a merge vertex, I can draw the diagonal at that point. Okay, so I'm going to draw the diagonal of merge vertices later when I replace the helper vertices of that edge. What if I never update their helper? Like in the, let's get back to this previous polygon in which this vertex is lower than, I mean, this, at this point, EW ends, and there are no vertices here between the sweep line and this point. So the merge vertex is never updated. I mean, the helper vertex of this EW is never updated. So this merge vertex stays the helper vertex of this to the end. So what are we going to do then? But it will it be the helper vertex of, no, when at the next vertex, this will not be a valid helper vertex, because the next edge, this vertex is going to be the helper of this edge. But so that's not going to work. It will not be, because when you there will be what may happen is that, but it may be, can we use it as a helper vertex? That may be a solution. Let's think about this. That may work for some cases. So do we really need to, can we still keep this as the helper vertex of this edge, although the helper is this? I mean, this will violate our definition of a vertex that is the lowest one. I mean, keeping this as the merge helper vertex of this one violates our original definition of helper vertex, but we may modify the definition. It may work. So we may need to work on this. We may make it work. I mean, we need to prove that there are no cases that really, both of them are good enough to be helper vertices.
The top vertex of the next stage is to the right.
Mm-hmm.
Past the merge vertex, then it will not work.
Yeah, okay. So there may be problems that it will not work. So that solution will not work. But one thing at this point, the solution that the book uses is this. When we come to the end of EW, and its helper vertex is never updated. So EW now is going to be deleted from the status tree. At this point, when we come here in the sweep line, EW is no longer going to be intersecting the sweep line, so EW is going to be deleted from the study structure. So at that point, we can do this. Can you see a safe diagonal that we can draw from the merge vertex? Yeah, to the end point of this EW, we can draw the diagonal. So even if the helper vertex is never updated, when I'm deleting EW, if I know that it's helper vertex during just that deletion, during that event point, when I come to this, as you can see, this is a regular vertex, this event point. And this regular vertex, if it's an endpoint of this line, and if the helper vertex of this EW was a merge vertex, I can draw a diagonal to this merge vertex easily, because I can, since it was always the helper vertex, I'm going to be sure that this diagonal from this end of this EW to this merge vertex is never going to intersect another polygon edge.
Hocam, en yakın olması gibi bir kaygınız yok mu?
No. Our only concern is that it shouldn't intersect any. So we are not. So that's a very good point. Up to now, we are trying to triangulate something, and I mean this is for dividing the polygon into monotone pieces, but we haven't actually talked about the quality of triangulations. Okay, so what does it mean, the quality of triangulations? One, for example, may want to have triangles in which the edges of the triangles have almost equal, not equal, but let's call them fat triangles and thin triangles. I mean, you can have a triangulation in which the triangles may have very long edges and one very short edge. So the difference between edge lengths may be a lot, okay? So it may be a very thin triangle. But maybe with another triangulation, you may avoid such triangles. So, but at this point in this problem, we haven't even touched to that problem. I mean, we are not worried about the quality, and this quality means that, I mean, triangulation, which provide more fatter triangles, a more large number of fat triangles may be considered a better triangulation than a triangulation that produces many long triangles that goes far between far vertices. But still, it's also a triangulation. So at this point, we are not worried about this. Later, we are going to see a triangulation method, which is called Delaunay triangulation. And this Delaunay triangulation is going to provide better quality triangulations. But at this point, we are not worried about this. Okay, just any triangulation works for us, as long as, I mean, any diagonal that doesn't intersect polygon edges is a valid diagonal for us. Okay, so this will be a safe edge for us, a merge vertex connected to the end of EW. So this actually completes our solution. We now know how to handle split vertices and merge vertices. Merge vertices are either we draw the diagonal, either when we come to the end of its edge whose helper vertex is this merge vertex, or whenever this merge vertex is replaced by another helper vertex. If this merge vertex is replaced by another helper vertex, we are going to draw a diagonal between these new helper and the merge. If it's not updated, we are going to draw a diagonal to the end of this edge. So after we know we draw these diagonals, our polygon is split into Y monotone pieces. So that's the final algorithm considers all is like this, the final algorithm. The main algorithm is like this. First of all, since in order to have plane sweep, we need to have our vertices sorted in Y coordinates, and our event Q is static, it doesn't change. The number of vertices of the polygon stays the same all the time, and that's the only thing in our event Q, the vertices. So we sort the vertices of the polygons in terms of their Y coordinate first, and then this becomes our event Q. And during plane sweep, we maintain which edges intersect the sweep line, and we put them in a binary search tree, in a balanced binary search tree, the edges that intersect the sweep line. And for each edge, and also we don't need to store edges, the right edges in which the polygon lies to their left. For example, during the plane sweep here, I don't need to store this edge in my study structure, because I know that it will never be the left neighbor of any event point, because this part is outside. Another edge here is going to be the left neighbor of this one. This may never be the immediate left neighbor of any event point, because it's going to be, I mean, that point has to be at the outside of the polygon. Okay, so if a point that in which this one is the left neighbor is a point that is outside the polygon. Okay, so we are not interested in such points. So we don't need to store this one or this one. So these black edges need not be stored. We only store the edges in which the polygon lies to their right in this global orientation. So when we store these edges, And when an edge is inserted in the study structure, we initialize its helper vertex to be its top vertex. So initially its helper vertex is top vertex. And whenever we come to a vertex, we look at its leftmost neighbor and we update its leftmost neighbor with this one. For example, this one may even be the helper vertex of this one. Okay, so although it is far away, but at this point it is going to be this. Whenever an edge is deleted from the queue, whenever we come to the end point of an edge, it's going to be deleted from the study structure. So the study structure always maintains the list of edges from left to right that currently intersect the sweep line. And we handle each of these 5 different types of vertices: start vertices, end vertices, regular vertices, merge and split vertices separately. We write 5 separate functions to handle these vertices. And it doesn't mean that we do nothing at regular vertices. Regular vertices are also important. We do a lot of things at regular vertices. For example, a regular vertex may be the helper vertex of some vertex. So even we may draw a diagonal at a regular vertex. Because if the previous helper vertex of that edge was a merge vertex, we draw a diagonal at a regular event point. So regular vertices, the only thing, I mean, in general, this is the thing we need to be careful in the algorithm. We need to delete edges and insert edges to the study structure based on whether it's the top or bottom edge of that vertex. And also, we need to determine whether we need to draw a diagonal or not. For split vertices, this is always the case. For split vertex, we know that we are going to draw a diagonal. Without asking anything, without looking at any condition, we draw a diagonal to the helper vertex of its left neighbor. Okay, so this is what we do at split vertices. For regular vertices, we may draw diagonals, and for merge vertices, we can a merge vertex will replace a merge vertex may be the helper vertex of some edge. We are going to correctly update that, and this may be the case that a merge vertex, when it's replacing the helper vertex, the replaced helper vertex may also be another merge vertex. Okay, so it may be you may draw a diagonal between 2 merge vertices. Okay, so this may be the case, for example, like this. So this is a merge vertex, so this is the inside. So there may be another merge vertex here, okay? And this is how the polygon is, okay? Okay, so this is, let's see, this is my polygon, okay? Look at this edge, EI. This is the merge vertex, merge 1. This is merge 2, okay? At this event point, merge 2 replaces the helper, so the helper of EI becomes M2 at this event point. And at this point, we look at what was the previous helper vertex. Previously, helper EI was M1. At this point, M1 becomes the helper vertex of EI, this one. But when M2 is replacing M1, it sees that, oops, the previous vertex was a merge vertex. So what do you need to do? You need to draw a diagonal, okay? And this diagonal gets rid of the merge vertex property of M1. We haven't, this M2 is still a merge vertex, okay? At this point, when we draw this diagonal, we got rid of M1 as a merge vertex. But M2 here, as you can see, both of its neighbors are still at the top, so it's still a merge vertex. So when will we get rid of this M2? When we draw a diagonal to something at the bottom. Okay, so that's so this is how the final algorithm is going to look like. And yes. So when it's split vertex, we always draw a diagonal to some helper vertex at the top. Okay, split vertices are handled as soon as we discover split vertices, but merged vertices are handled later. Yes. A merged vertex can be split with a. Yeah, it can. Yeah, actually, that's a good example. So we may get rid of two vertices at the same time if the one that is upper is a merged vertex and the one that is lower is a split vertex. If we draw when we are getting rid of the split vertex, if the previous vertex was a merged vertex, it means that we also got rid of the merged vertex. Yes, and this you can easily draw an example that has such kind of a thing. For example, it could have been like this. So this is a merged vertex. This is the inside of the polygon, and this is going to be a split vertex, and this is the inside of the polygon, right? Yes. So let's try to. Yeah, it can be done. So for example, it's here like this. At this point, no, the split vertex should be at down. Okay, so you need to draw something like this at the down, and you need to have an edge here. So this one is going to be the helper vertex of this one. The split vertex, when we come to here, we are going to draw a diagonal from split to the merge, which is going to get rid of both. Other questions? And in terms of time complexity of this problem, the sorting of the y coordinates, our event queue, is going to take n log n time. So we'll need to sort by their y coordinates. Since it's a simple polygon, I don't know whether you can do it in linear time. Actually, let's see. The book maybe says even that part may be linear time. Let's see. Yeah, actually the priority queue takes linear time, but I didn't understand actually that point. Given a simple polygon, it may be concave, it may be as complex as this. Can you have the event queue in linear time? The thing is, you are given this polygon as the vertices are ordered, either counterclockwise or clockwise, but on the boundary of the polygon. Okay, they are ordered on the boundary of the polygon. So there is some order between the vertices. They are not just random points. I mean, they are organized somehow on the boundary of the polygon. By using this organization, by using this ordering on the boundary of the polygon, can you order them with respect to their y coordinates in linear time? I mean, I don't know the answer to this question, but the book says it can be done in linear time. So I'm as if maybe it's something trivial. I mean, it doesn't explain how it is done in linear time, but I don't see the solution to this instantly. I mean, you need to think about this. I don't know whether it's possible or not. I mean, right now it seems impossible to me. It seems like a very difficult problem to have the vertices in y coordinates. Maybe it can be done. I don't know.
Everything will be changed. We can calculate the y coordinate and we can add it to an array, let's say, as if we assume it starts from 0 and goes increases. So not array, but like a hash table. So we will use the y coordinate as hash and
Okay.
we'll just add it until we finish all of the.
Okay, so if you assume, for example, I mean, let's forget about the degenerate cases again. Let's assume no two vertices have the same y coordinates. Okay, I mean, assume that there's an order between all the vertices, then if you know the minimum and maximum y coordinates, you can have an array of all the y coordinates and fill in the vertices which have that y coordinate. Maybe, yeah, maybe that's a good idea. Some hash table entries may be left empty, but it's not a problem. So if you know your bounds, minimum y and maximum y bound, you can fill in the by going over these, you can fill in the, I think this is how they do it.
If we use something like a linked list or expandable array, so we do not need to know the bounds.
Okay. Okay. You don't need to even know the bounds. If I mean, this is like actually the doubly connected edge list is like a linked list. So it is if the simple polygon is given to you as a doubly connected edge list, you'll be able to start with any from any vertex and do it. Okay, but that's linear time. But what happens is that our study structure, when we are having the sweep line, when we insert the edges on the sweep line, each of the query of the leftmost neighbor take log n time. And if we do it for n vertices, at the end the overall complexity is going to be n log n, due to during sweep line we need to find out which edges intersect the sweep line in a certain order, and we need to do query. Given a vertex, given a new point on the sweep line, we need to query an edge in this binary search tree. And this query is going to take log n time. And we may need to do this query n times for each vertices at the sweep line. So the time complexity of n log n comes from that. So if you already have n log n, you don't need to worry about doing the first processing with n. You can also sort the y coordinates in n log n, so which is not going to change the overall time complexity. Okay, so our conclusion is that simple polygon can be triangulated in n log n time, and not triangulated, sorry. It can be decomposed into y monotone pieces in n log n time. And after the break, we are going to see an algorithm a linear time algorithm to triangulate a y monotone polygon. It's a very simple algorithm. It's going to take half an hour to describe. And we are going to start with the new chapter after that. Okay, so let's have a 10-minute break.